Hello, my name is Stephen Schockaert, and this tutorial talks about how natural language processing systems and NLP systems can access background knowledge about the world. So the state of the art in natural language processing is based on these so-called language models. And these current systems based on language models typically don't use any explicit knowledge bases. Somehow the knowledge that they need is already captured implicitly by these language models. So in this tutorial, I want to explore what kind of knowledge these language models are capturing and what kind of reasonings they can do. Now, before talking about language models, I just want to say a little bit more about the traditional way in which word meaning has been captured in natural language processing systems. So the main idea is that the meaning of a word is represented as a vector. And the traditional way has been to learn these vectors based on co-occurrence statistics. So for example, if we have a vocabulary of 4 million words, then each word would be represented as a vector with 4 million coordinates. And these coordinates would basically capture statistics about how often two different words co-occur. So for example, if you have a word like apple, then that word often co-occurs with tree. So in the vector representation of apple, the coordinate corresponds to tree, we would expect to see a high value. Similarly, we would expect to see high values for fruit and other words that are related to apple. And the same for other words. There are different ways in which you could actually measure the strength of association. An obvious way would be to represent in these vectors the number of times two words co-occur in a large text collection. For example, how often they appear within 5 words or within 10 words of each other. But there are a lot of other approaches that can be taken. And in particular, this idea of using the pointwise mutual information or the positive pointwise mutual information is one that seems to work well in practice. Now, the problem with just using co-occurrence statistics is that this gives us vectors which are very high dimensional. So that's not very practical to use. So people have come up with different ways for reducing the dimensionality of these vectors. One of the, probably the first approach to do that was latent semantic analysis, which uses a matrix factorization technique called singular value decomposition to go from the high dimensional the 4 million dimensional space to a much lower dimensional space of, for example, 300 dimensions. In this case, the coordinates of the vector now are sort of latent values. They don't have a clear meaning anymore, but we have a compact representation that somehow captures all the important information that was captured in the very high dimensional co-occurrence-based vector. Since the LSA model, a lot of different approaches have been proposed, especially in the last 7 years or so, starting from the skipgram model that uses sort of very simple neural network based prediction model to learn these low dimensional vectors, and the glove model that uses a sort of least squares regression approach. And one of the reasons why these word vectors have become so popular in the last few years is that they make it very convenient to build natural language processing systems using neural networks. So the basic idea is that we start from a given text fragment. Each of the words in a text fragment can be represented as a vector, so the text fragment itself can be represented as a sequence of word vectors. And then we can use something like a recurrent neural network that somehow learns a transformation of these vectors onto something that we want to predict. In the case of this example, it could be a sentiment prediction. So to what extent is a review positive or negative? Now, going back to the main topic of this tutorial, an interesting thing about word vectors is that they seem to capture a lot of world knowledge that we may not intuitively expect to be covered by these or captured by these word vectors. So this is a figure here from the paper that introduced the skipgram model, showing that somehow word vectors capture the capital of relationship. So in particular, the vector that connects the name of a country with the name of its capital seems to be more or less constant. So at least for different countries, the vector that connects the country to the capital tends to be quite similar. So that allows us to use word vectors to predict for a given country what is its capital. And it turns out that this doesn't only hold for the capital of relationship. There are quite a lot of aspects of world knowledge that are captured by these word vectors. So the same holds for syntactic relations. So the vector from quick to quickly, for example, is pretty similar to the vector from slow to slowly. But also a lot of encyclopedic knowledge is captured. So the vector from Belgium to Brussels Airlines is similar to the vector from Greece to Aegean Airlines. Or the vector from Steve Ballmer to Microsoft is similar to the vector from Larry Page to Google. And it doesn't only work with vector differences. We can also sort of add up vectors. If we add up Russia and river, we approximately get the vector for the Volga River. If we add up Germany and capital, we approximately get Berlin. If we add Czech and currency, we approximately get Koruna. And in fact, there have been a lot of papers that have shown very remarkable properties of word vectors. So there's a lot of world knowledge that we can somehow predict based on word vectors beyond what we would intuitively expect. Okay, so now we get to the main topic of this tutorial, which is language models. Now, the point of a language model is to capture the meaning of language, but rather than word vectors, these language models operate at sentence level. So basically what happens is that we take a sentence, so in this case, a mouse took a stroll through the deep dark wood. Each of the words of that sentence is represented as a kind of vector. That vector goes into a deep neural network, which follows an architecture that is called the transformer. And at the end, we again have one vector for each word, which is called a contextualized word vector. It's called a contextualized word vector because that vector does not only depend on the word at that position in the sentence itself, but also on the rest of the sentence. So intuitively, it captures the meaning of that word in the context of that particular sentence. The way these models are trained is basically by taking sentences from a large text collection like Wikipedia, replacing one or several of the words in that sentence by a special token called mask, and then training the network to learn to predict which words are missing, so which words should occur at the masked positions. And in this way, implicitly, the model learns about syntactic structure because it needs to predict a word that grammatically makes sense in the sentence, but it also needs to learn a lot of background knowledge, a lot of common sense and semantic knowledge to learn to predict these words accurately. And to use these models in practice, what we typically do is, and so this is called fine-tuning, we take the final layer, the final vectors predicted by the model, and we learn one last transformation. Typically, that's a very simple transformation, maybe just a linear transformation, although in theory it could be any type of neural network that in the end predicts whatever we want to predict in a given application. So for example, the sentiment of a text fragment. And so the idea is that this final transformation is learned, and at the same time, the weights of the language model itself are adapted. So we fine-tune the language model, we adapt the language model to a particular target task. Now, it turns out that these language models work really well in practice, so they have really changed the state of the art in natural language processing. But for this tutorial, what is most remarkable is that actually these models capture a lot of knowledge. And so just to give you an illustration of this, what you see here on the slide are the results of a recent language model called T5, where they show that they can use the language model to answer questions. And so they considered 3 question answering benchmarks. They fine-tune the language model such that if you use a certain question as the input to the model, it will give you the answer. And it answered that question in particular without access to any external knowledge. Now this is different from the baselines to which they compare here, which typically work as follows. You take a question, you retrieve relevant documents from a large text collection, let's say Wikipedia, and then you try to extract the answer from the text fragments that have been retrieved. Right? So that's the typical way in which you would do question answering. In contrast, the results that you see for T5 don't use that external text collection at all. They just train the language model to directly give you the answer. So whatever questions can be answered in this way, if a given question can be answered in this way, it must mean that the knowledge that's needed to answer that question is already captured in the parameters of the language model itself. And as you can see from these results, actually that works quite well. In many cases, you can achieve state-of-the-art results, and even in cases where you don't, you actually get very close to state-of-the-art results, provided that you use a big language model. So the last one, the best performing one in this table, has 11 billion parameters. So that's a very deep language model. So it's clear that for this to work well, we need a very large language model. But if we do manage to train this very big language model, it captures a lot of knowledge. And I mean, this is really remarkable, right? Somehow, the parameters of that neural network implicitly capture sort of most of the knowledge that is described in an encyclopedia like Wikipedia, for example, or in even a bigger document collection. Now, as remarkable as this is, for factual knowledge, we can sort of understand that if it has seen certain types of knowledge during training, somehow in the parameters of that model, that knowledge is memorized, and we can sort of use the language model as a sort of associative memory, where if you give the right question, it can sort of retrieve that knowledge that it has memorized. Now, a bigger challenge is common sense knowledge. So is the language model, after having been trained on a large text collection, able to capture common sense knowledge that may not actually be explicitly described in a collection like Wikipedia? So that's the question I want to focus on in this next part of the tutorial. Now, when we talk about common sense knowledge in the context of knowledge representation, I mean, the typical example is Tweety the bird, who is also a penguin. So this is, the standard example to analyze the capability of systems to do non-monotonic reasoning. So I couldn't resist trying out whether a typical language model, in this case GPT-2, would be able to understand that birds are able to fly, but penguins are not, despite being birds. So GPT-2 is a model that has been trained to complete a certain initial part of a sentence. So you give it the initial part, and in this case, I tried 3 different versions. So the first one, we say, Tweety, a bird, sat on the side of the road. When he got bored, and then we ask the language model to complete that sentence. Second version of the sentence, Tweety, a robin, sat on the side of the road. When he got bored, and then the language model is supposed to complete that sentence. And then in the last case, we say, Tweety, a penguin, sat on the side of the road. When he got bored, and then again we ask the language model to complete the sentence. So what we would expect is that in the first 2 cases, maybe the model says, well, he flew away. Whereas in the last case, obviously, we don't want the model to predict he flew away, because penguins are not able to fly. Now, what you can see here is the actual answers I got with GPT-2. And actually, if you're interested in this, you can easily play with these models using the link I put at the bottom of the slide. So what I got was the following. For the first case, so Tweety, a bird, and so on, he would fly off to the other side of the road and sit there. So pretty interesting response, which seems to be perfectly fine in terms of common sense behavior. For Tweety, a robin, we again get that he would fly off and land on the road again. So again, that's perfectly acceptable. And interesting, for Tweety the penguin, the response we get is different, because now we say, now GPT-2 says that Tweety would hop up and down on his hind legs. So somehow it seems to realize that it shouldn't predict that Tweety the penguin would fly away. So that's pretty interesting, and to be honest, I didn't really expect this to happen. So I decided to make the problem a little bit harder. So now the 2 sentences mention both that Tweety is a penguin and that he is a bird. Right? So the first sentence says, Tweety, a penguin, sat on the side of the road. When he got bored, being a bird, he, and so on. And the second sentence says basically the opposite. Tweety, a bird, sat on the side of the road. When he got bored, being a penguin, he, and so on. Now, recently, a successor to the GPT-2 model was proposed, which is called GPT-3. And GPT-3 is basically the same as GPT-2, but it's a lot bigger. So it's a lot more parameters. It has 175 billion parameters, and it was trained on a much bigger text collection. I think around 500 billion tokens of text. And as a result, simply by sort of taking this brute force approach of having a bigger model trained on more data, it actually is a much better model. So whatever common sense reasoning abilities GPT-2 already had, GPT-3 seems to be even more impressive. Now GPT-3 is not openly available, but some people who have early access to this model have done some tests, in particular also for common sense reasoning. So this is this example, and the next examples I will show are the experiments that were done by Ernest Davies and Gary Marcus. And I think they're quite interesting. And if you're interested in this, if you look at the link at the bottom of the slides, there you can see many, many more examples of experiments like this. So the idea is always the same. We give GPT-3 an initial text. So in this case, that's the text shown in black. And then it has to finish the story. And that's the colored bit at the end. So here, the prompt, the text that we give GPT-3 is this. You are making coffee with milk and sugar. You don't have a spoon to stir your coffee, so you stir it with a pen. But that turns out to be a bad idea because the coffee, so that's the part that GPT-3 was given. And then the language model completes, the coffee is too hot and the pan starts to melt. So that's, pretty good and pretty interesting behavior. So here's another example. At the party, I poured myself a glass of lemonade, but it turned out to be too sour. So I added a little sugar. I didn't see a spoon handy, so I stirred it with a cookie. But that turned out to be a bad idea because, and again, so this is the part that was provided to GPT-3, and then GPT-3 completed as follows, because the cookie crumbled and made the lemonade cloudy. So I tried to fish it out. So I tried to fish out the crumbs with a fork, but I couldn't get them all, and I ended up drinking a lot of crumbs. So this is really very unexpected and a very interesting type of response, and it shows how much can be achieved with these modern language models if you train them on a large enough text collection and give them enough parameters. Now GPT-3 doesn't always get it right, and actually if you go to the website at the link at the bottom of the slide, I think that in about half of the cases the answer is actually not correct. So here's just one example of a case where GPT-3 gets it spectacularly wrong. So the story is this. You poured yourself a glass of cranberry juice, but then absent-mindedly you poured a teaspoon of grape juice into it. It looks okay. You try sniffing it, but you have a bad cold, so you can't smell anything. You're very thirsty, so you, and then GPT-3 completes the story, drink it. You are now dead. So obviously this doesn't make any sense at all, and basically, the language model was fooled by the story that seemed to suggest that drinking that glass was somehow dangerous, right? The author is very reluctant to try it, but in the end, decides to take a risk. And what GPT-3 doesn't seem to realize is that grape juice is actually perfectly fine. So it sort of uses these shallow linguistic clues to sort of guess that probably it was a bad thing to do this, and it guesses that you are now dead. So that doesn't make any sense. So here's an example of another experiment with GPT-3. So here, the prompt, so the part of the text that's given to GPT-3 before it has to start completing things is a bit longer. And the aim of this prompt is to explain to GPT-3 that you wanted to answer questions. So all this does is to show GPT-3 the format of how you want to interact with it. So you have this Q&A format with some random factual questions. What is the human life expectancy in the United States? Answer: human life expectancy in the United States is 78 years. So you give it a few questions and answers like that, and then so you follow with a question, but no longer the answer, right? So now you give it the first question: what is your favorite animal? And then, so in this case, everything in bold is what GPT-3 completed, right? So you give the questions and the answers from the previous slide. You give it the question: what is your favorite animal? And then GPT-3 completes answer: my favorite animal is a dog. Okay, so far so good. Next question: why? So that's again given by the author of the test. And then after the question why, again GPT-3 has to answer. So GPT-3 completes the text as follows: because dogs are loyal and friendly. Again, pretty good. Next question: what are 2 reasons that a dog might be in a bad mood? GPT-3 answers: 2 reasons that the dog might be in a bad mood are if it is hungry or if it is hot. So here, this is quite remarkable, right? Because it seems to understand quite a lot about dogs. Okay, next question. How many eyes does a giraffe have? Answered by GPT-3, a giraffe has 2 eyes. Very good. Next question. How many legs does a frog have? The answer that GPT-3 gives, a frog has 4 legs. And so on. Are there any animals with 3 legs? No, there are no animals with 3 legs. Next question. Why don't animals have 3 legs? Answer. Animals don't have 3 legs because they would fall over. So this is very, at least in my view, very remarkable, because this model, it was not trained to answer questions. This was a language model that was simply trained on a lot of text, trying to complete random sentences. And somehow it has learned not only to recognize this question answering structure, so it doesn't only realize that if you give it a question, it should answer, but it actually knows how to give you pretty reasonable answers. Now, where GPT-3 starts to struggle is if you ask it nonsensical questions. So here, the first question, how many eyes does a giraffe have? Okay, it answers you, a giraffe has 2 eyes. But then if you ask it, how many eyes does my foot have? It answers, your foot has 2 eyes. So it doesn't recognize that this is a nonsensical question. How many eyes does a spider have? Here it says a spider has 8 eyes. Now, here it seems to answer 8 because usually when you ask how many and spider in the same sentence, then typically the question would be about legs, and probably that somehow confused GPT-3. And the next one is completely nonsensical again. How many eyes does the sun have? The sun has 1 eye. And then how many eyes does a blade of grass have? A blade of grass has 1 eye. And then here we have completely nonsensical questions, like how do you sporcle a morgul? And then GPT-3, not realizing that this is nonsensical, tries to guess, right? And in this case, it answers, you sporcle a morgul by using a sporcle. It makes no sense whatsoever. The third one is interesting as well. How many rainbows does it take to jump from Hawaii to 17? And GPT-3 helpfully answers, oh, it takes 2 rainbows to jump from Hawaii to 17. So clearly, it cannot recognize nonsensical questions. And this idea of GPT-3 struggling with unusual inputs is something that we've seen with other language models as well. So here is an experiment with another model called Roberta, and the task is so it's given a sentence with 2 ages, and it has to say whether one age is younger or older than the other one. So at the place where younger or older needs to be, there's a blank. The model predicts a vector, and then if that vector is more similar to the vector for younger, then we assume the model predicts younger. If it's more similar to the vector for older, we assume the model predicts older. And then we can look at how often does the language model give us the correct answers. So does it know that 20 years old is younger than 35 years old, for example? And it turns out that this Roberta model can actually do this pretty well, achieving an accuracy of 96% on this task. But then the authors of the paper noticed something strange, which is that as good as this model is, if you replace the numbers by numbers which are not in the typical age range, then suddenly the results collapse. So this is illustrated here in these diagrams. So what you can see, for example, in the top left corner, is for different combinations of ages when the model predicts younger. So this triangular shaped diagram corresponds to a nearly perfect result. But then if we change the ages by numbers that come from a year distribution, so at the bottom left corner, so for example, a 1980-year-old person age is, and then younger or older than a 1988-year-old person, the model collapses and it just always predicts younger. And so we get this sort of square shape. Okay, so it seems clear that language models can somehow capture common sense knowledge. Now, the next question I want to discuss is, can language models reason? Now, of course, reasoning can mean different things. Now, here in this first example, basically what is analyzed is whether the language model can compute logical consequences of factual information it has seen during training. So for this experiment, a synthetic corpus, a synthetic collection of text documents was generated where, for example, a particular relation might be transitive. So that means that if for an entity A and B, there's a factual statement in the text corpus that the relation holds between A and B, and we also have such a statement for the entities B and C, that typically then we would also see such a factual statement that says A and C are related, right? So if A and B are related, B and C are related, then A and C should be related as well. And so the idea is that if a particular relationship R is transitive, then for most of the factual information in the synthetically generated text collection, that transitive information is there, but not for all of them. So for the test examples, maybe the training corpus that was used for training the language model mentions that A is related to B and B is related to C, but it doesn't contain the fact that A is related to C. So the question in that case that we want to answer is, when we're using the language model after training, does it know that A should be related to C? So in this paper, they analyzed a number of different types of logical dependencies, so reflexivity, symmetry, inversion, composition, which has transitivity as a special case, equivalence, negation, and implication. The main finding is that when training BERT, this language model, on that synthetic corpus, it basically recognizes reflexivity, symmetry, and inversion. It also recognizes equivalence and the particular notion of implication that they consider, but it does not learn these composition relationships, not even in the special case where the composition relation is really a transitivity relation. And then they show that with certain tricks they can sort of make the model behave a little bit better, but basically composition, which is really from a logical point of view, a very basic type of rule, is something that the model was not able to capture. And then another one that was difficult to capture is negation. And actually a lot of other papers have also found that the BERT language model struggles with understanding negation, but more recent models like Roberta are able to handle negation actually quite a bit better. Now, a number of recent papers have also looked at whether it's possible to train language models that can reason with rules that are given in natural language. So in this case, we're not looking at zero-shot behavior. So that means we're not looking at how well the language model performs without further fine-tuning. The question is whether we can sort of fine-tune the language model such that it can do the kind of inferences that you can see in this example on the slide. So in this case, we are given a text fragment that first states a number of facts, like the bald eagle does not eat the dog, the cat chases the dog, and so on, followed by a number of rules, so sort of in an if-then format. So for example, if someone does not eat the cat, then they do not eat the dog. And then at the end, there are true or false questions that the language model has to answer. So does it follow from the information that is given that the bald eagle likes the cat, yes or no? Now, the results are summarized here in this table. So what you can see in the different columns are models that have been fine-tuned on problems of varying difficulty. So the first column, which has mod 0 in the heading, is a model that is trained only on fragments where the answer to the question is given as a fact. So the reasoning depth is 0. And the next one, so model 1, has seen during training examples where the answer has to be inferred using one inference step. So there's a fact and there's one rule that you have to apply to find the answer. And then similar for the other ones. So for model 2, for example, there would be 2 inference steps. So there's maybe a fact and you have to apply a rule, and then I have to apply another rule, and so on. And then the different rows correspond to test cases also of different reasoning depth. And so what we can see here is how well the model generalizes. So unsurprisingly, if during training the model only ever had to look at the factual information, it doesn't really learn how to reason. So the performance is quite bad. If it has seen inference change of length 1 during training, so that's the column which has as the heading mod 1, and again, it does not generalize much. So, I mean, because it has been trained like that, it is able to apply this one-step inferences also during on the test data, but it is not able to apply longer inference chains. But then if we go further, and in particular, if we look at this mod 3 that has seen examples that require 3 inference steps, then we can see that even in test data that require more than 3 inference steps, in particular 4 or 5 inference steps, that the model is able to solve these test cases correctly as well. Here's a paper that studies reasoning yet from another point of view. So here, this is an example of what is called natural language inference. So in this setting, we are given 2 sentences, and the model has to decide whether the first sentence entails the second sentence, whether it contradicts the second sentence, or whether there is no such logical relationships between the 2 sentences. And so they specifically looked at instances of this natural language inference problem that require particular forms of reasoning. So these forms of reasoning are shown here. So for example, if we look at the fragment that's called Boolean, then so the first sentence that's given says Travis, Arthur, Henry, and Dan have only visited Georgia. And the second sentence says Dan didn't visit Rwanda. And indeed, of course, the second sentence is a logical consequence of the first sentence, so the model should predict entailment. So if you look at the results in this table, so they're organized in 3 blocks. The first block contains the baselines. So for example, the second one, the hypothesis only by LSTM, is a model that only sees the second sentence. So of course you cannot solve the task by only seeing one of the 2 sentences, but still the model is able to achieve almost 50% accuracy. So where random guessing would be 33% accuracy. So that means that there are some biases, some artifacts in the dataset that can be exploited. So anything below 50% is therefore considered to be a weak result. If you look at the language model, so the second block, we see results for the BERT language model. And this is a language model that has been pre-trained on standard natural language inference datasets. So they have been fine-tuned to understand the nature of the task, to understand how we can predict entailment, contradiction, and the neutral relationship, but they have been trained on data sets that don't follow that sort of syntactic logical structure that is considered in the test data, but more natural examples. And so it shows that these standard natural language inference data sets are not sufficient to teach a model how to do these logical inferences, because the performance of these BERT classifiers is below 50%. But then, as you can see in the last block, if we fine-tune the BERT language model on data that follows the same distribution as the test data, so on these sort of logical examples, then actually it's very easy for BERT to learn to recognize these inference patterns and to apply these inference patterns. Right? So the conclusion here is that the types of inference that are considered in the paper, that language models may not be able to do them out of the box, but it's very easy to fine-tune a language model to learn to recognize these kind of patterns. So I think the conclusion from the previous few papers is that reasoning remains challenging for language models, but at the same time, it also seems that it is possible to teach language models to do at least basic forms of reasoning. So a natural question that we may ask ourselves now is, do we still need structured representations? Do we still need to worry about creating knowledge bases, structured knowledge bases, and making them available to natural language processing systems? Or is it enough to focus on how we can better train language models, maybe train bigger language models, maybe find small variations to how these language models are fine-tuned at the moment, and then hope that, in some way, these language models can do all the reasoning that we need in actual applications. So this is the last part of this presentation which will try to get some insights into this question. Do we still need structured representations of knowledge? Now, one reason why structured representations are still important is highlighted in this paper. So what they did here was to create a collection of stories which somehow explain how different people are related to each other, so family relationships. And then the model has to answer questions about how different people are related. So in this example here, we have a story that says that Kristen and her son Justin, so Justin is the son of Kristen, went to visit her mother Carol. So Carol is the mother of Kristen, and so on and so on. And so from this information, we have to answer the question, how is Carol related to Justin? And the answer, of course, is that Carol is the grandmother of Justin. So to do well on this task, the model has to understand the basic language that is used, but also it has to learn how to compose family relationships, right? So it has to know that, the mother of your mother is your grandmother, for example. And so in this paper, they compared how different existing models for question answering perform on this task. So they were given a lot of training examples, a lot of examples of stories with associated questions. And then they trained models, so one based on BERT, one based on BiLSTMs, or actually two based on BiLSTMs, two based on BERT. And then one that is based on graph structure, so GATs, gated attention networks. And so this model is different because rather than being given the story as a sequence of sentences, it was given a graph representation of the story, right? So it somehow has an advantage. But if, for example, the BERT model is able to do reasoning, it should be able to do as well as this graph-based model. And so the results that you can see here show you the accuracy of the different models as a function of the relation length, so the number of sort of inference steps that the model needs to make in order to make the correct prediction. And on the left-hand side, you can see the result of a model that was trained on stories that only need 2 or 3 inference steps. And on the right-hand side, you can see what happens if we have 2, 3, or 4 inference steps in the training data. So on the left-hand side, pretty much all the models perform poorly. On the right-hand side, we can see that the gated attention network actually becomes a lot better. So it does well on test examples that need 2, 3, or 4 inference steps. But it also continues to do quite well with 5, 6, and then of course it gradually decreases. Now the interesting lesson here is that the BERT model, which is shown in blue, is actually performing very poorly. It's the worst performer of all. And so that shows that without any sort of inductive bias, without the structural information that there are people who are related in some way, and what we are really after is the composition of these relationships, that this BERT model apparently cannot generalize. It cannot learn to make these kinds of predictions. So here's an example of another type of model that relies on graph structures. So here the idea is that we want to answer a question that requires us to combine information from multiple documents. And the approach they take in this paper is to learn a knowledge graph that integrates the information from the 2 documents. So they have some heuristics and some reasoning to do disambiguation and to find out how the entities from the different documents relate to each other. So that's a sort of pre-processing step. And then once they've generated this knowledge graph, they sort of write almost like a story that describes the knowledge graph. So they encode the knowledge graph as a sequence of words, and then they train a language model to take that sequence of words as inputs and use it to answer the actual question. So the graph representation in this case is used as an intermediate representation that allows them to do some kind of pre-processing when fusing the different documents, and then feeding the resulting graph as input to the question answering model. Another possibility which has been considered by a lot of different people is to start with a given knowledge graph. In the case of this paper, the knowledge graph is ConceptNet, and to make the information from that knowledge graph available to the language model, right? So in this case, they look at a question answering task that requires common sense inference. And what they do is they find paths in the ConceptNet graph that link words or concepts from the question to possible answers to the question, and use an encoding, a vector encoding of these paths in ConceptNet as additional information that is used together with a fine-tuned BERT language model. So the idea in these kind of papers is that existing knowledge graphs can be used as a sort of external knowledge repository that it has useful information that can be used in combination with a standard language model approach. So in the previous slides, I gave examples of approaches that show that structured knowledge graphs are still useful. In this paper, they do something different. What they basically show is that you can fine-tune a language model based on a given knowledge graph. So they did experiments with two common sense knowledge graphs, Atomic, which is shown at the top here, which is a knowledge graph about everyday events, and ConceptNet, which is a well-known common sense knowledge graph. So the idea is that each of the triples from the knowledge graph is sort of represented as a kind of sentence. They train the language model based on these types of sentences, and then once the model has been trained, it can be seen as a neural encoding of what was already in the knowledge graph, so it can sort of remember the triples that were in the original knowledge graphs. But interestingly, it can also generate new triples that were not in the original knowledge graphs. So lexical variations, so different ways of describing the new event, and to some extent it seems also genuinely new triples, so capturing knowledge that was not explicitly given in the original knowledge graphs. Now in this paper they go one step further, and so they show that an important advantage of these neural encodings of common sense knowledge graphs is that you can apply them to a given text fragment. So rather than using these models for knowledge graph completion, what they do is they start with a story, and then they use the language model encoding of the atomic common sense knowledge graph to find out possible consequences of things that have happened in the story. And the other interesting thing about this paper is that they do this sort of iteratively. So they have the initial story, and they use their model to make predictions that can be made from the initial story. So they have a number of additional facts. Now for each of these additional facts, they have a longer story, right? So the initial story with the predicted fact. And then they can run the model again to predict another fact, and then another fact, and another fact. So what we get in this way are really inference chains, where the model does predictions not as a one-off process, but iteratively predicts sort of what happens then and what's the consequence of this, and computes a chain of predictions in this way. And so they show that if they do a sort of probabilistic reasoning on top of these chains of predictions, they can get better results on the evaluation tasks that they consider in this paper than if they use the model as a sort of one-off prediction. So the interesting thing here is that even though they don't need structured representations anymore as part of the input, because they have a language model that encodes the initial knowledge graph, the atomic knowledge graph, they still end up with a sort of structured graph representation which they need as part of the reasoning process. So to conclude, we talked about 3 questions, and I think none of these questions have a clear answer, but we have some information. So do language models capture common sense knowledge? To some extent, yes. Actually, the common sense reasoning abilities of recent models is really quite remarkable, but there are limitations. If you ask them nonsensical questions, you get nonsensical answers. As for the second questions, can language models reason? It seems clear that language models can be fine-tuned to do basic forms of reasoning, so basic forward chaining, for example. More complex forms of reasoning are probably too hard for current models. And also there's a problem with systematic generalization. So that is also a clear limitation. And the third question, do we still need structured representations? So here there's a couple of answers. Graph representations seem to help for better generalization, and they seem to help for collating evidence from multiple documents. Structured representation can also be useful for injecting external knowledge, so from knowledge graphs, to make it available to a particular application. But on the other hand, such knowledge can also be, at least to a large extent, encoded in the language model itself. And then the final example I gave was basically about using graph representations to allow for a more systematic reasoning process than language models on their own would be able to do.